So let's begin. Hi guys, I wish everyone a pleasant evening here. My name is Rehber and I'll be your guide for today's event, along with my friend and colleague Ariman. So before we begin the event, I'd like to take this opportunity and thank my seniors for believing in us. And I'd also like to thank you guys for making time for this event, especially after a day's worth of classes and on a Friday night. Well, the motivation behind this event is pretty straightforward. We want to introduce complicated topics that most people are afraid of in an approachable and easy to understand way. As far as prerequisites are concerned, this event has none. Regardless of your background and past knowledge, we guarantee that you will take something back from this event and enjoy learning about it. So without further ado, let's get to it. So let's start talking about cryptography. So cryptography 101. We've all used various products and services that employ the use of cryptography. A few notable ones include WhatsApp, YouTube, Gmail, and MS Teams, just to name a few. So you might wonder, why do we need to encrypt our data? Well, to explain that, let me take an example. We've all had guests coming over to our house, wholly uninvited, snooping around in our private family matters. These nifty algorithms that we'll be talking about today will prevent our online presence from being intercepted and listened to by such unwanted guests. The photo on your screens paints a clear picture on how our data gets encrypted before being transmitted across the internet. This might not be something new for the most of us here, but for the sake of taking everyone along for this ride, let's discuss it on a very high level. As a matter of fact, this slide that you're reading right now is only visible to you after it has been encrypted, and then it goes through a series of servers and then finally to your ISP, who sends it over to your device where it gets decrypted before you get to see it. Now, if this whole thing gets intercepted midway without the proper decryption taking place, this is what a person will be able to see. Utter garbage, right? Like nothing worthwhile will be able they'll be able to see. Now, next we'll be talking about ciphers and their historical significance. Like, why should we even know about the past, right? So let us turn back time like Dr. Strange and see more about ciphers and cryptography used in the past. We promise that this won't be a boring history lesson. The past, right? In the early 20th century, the invention of complex mechanical and electromechanical machines, such as the Enigma rotor machine, provided more sophisticated and efficient means of encryption. But encryption as a concept is way older than that. The ancient Greeks are said to have known of ciphers. The Spartan military used the Citale transposition cipher, but it's not definitively known whether the Citale was used for encryption, authentication, or avoiding bad omens in speech. Here's an example of how one looked like. Next, we shall talk about polyalphabetic ciphers, more specifically the Vineyard cipher. A polyalphabetic cipher is any cipher based on substitution using multiple substitution alphabets. Here is a simulation on how the Vineyard cipher encodes plain text. We have provided a link in the chat box for you right now for you to go and play with it for yourselves. The Enigma machine is more complex, but is fundamentally a polyalphabetic substitution cipher. We shall learn about the Enigma a little bit later on. Well, if none of this made any sense to you, the TLDR for this is that ciphers have been a quintessential part of history, so it makes sense for us to take some design cues from them and possibly make our own cipher. Next, we shall learn about Caesar cipher. If, like me, you also attended a school with a CIC affiliation, you know exactly what I'll be talking about right now. Well, in cryptography, a Caesar cipher is also known as Caesar's cipher, the shift cipher, or Caesar's code. It is one of the simplest and most widely known encryption techniques. It's a type of substitution cipher in which each letter in the plain text is replaced by a letter some fixed number of positions down the alphabet. Here you can see how the text first gets shifted and then it is replaced by some alphabet that coincides with the current position. For example, here I've used the word hello, and you can see that the whole alphabet got shifted by 3 positions, and then its corresponding positions are only highlighted in the actual encoded text. Now here is an example on how it was used in the Great Holy Roman Empire. There would be two disks, right? One on top of the other. There would be a big one and there would be a small one. And then what would happen is that the outer disk, right, would be turned the number of times you want the key to be as. In this case, we have taken the key to be 7, right? So what happens is that whatever text you want will be like swapped by 7 positions, something like this. Now I'll be inserting some text over here for you, and then you'll be able to see what actually happens. You'll see that all the letters over here are shifted by exactly 7 spaces, right? Now, if you are more interested in like playing around with this tool for yourself, you can see that there must be a link in the chat box. Again, you can go and play with that. Unfortunately, with all single alphabet substitution cipher, the Caesar cipher is easily broken, and in modern practice, it offers essentially no communication security. Well, if you were wondering about the tool we used, like I said, the link will be available in the chat box, and you can fiddle around with it. It is made by our peeps at the ACM chapter of the UCLA. Now let us hop on to the next cipher, that is the skip cipher. Well, the skip cipher or the jump cipher is another transposition cipher, just like the ciphers. This type of cipher reorders the letters of the message by extracting every n characters or by jumping every n or skipping n minus 1 characters. When the end of the message is reached, restarts to the beginning. Now, it sounds pretty complicated, right? It's actually not that hard to understand. All you need is the help of an example. Let us take this message. The message is decode, D-C-O-D-E. Now, this message is to be encrypted with a jump or skip value of 3. Now, starting with the first letter D, and then we'll move 3 positions, and we'll see that, okay, we found another D. Now, for the next letter C, we shall move and we'll find E, and next we'll go to the next letter, that will be O, and we'll continue to do so till we transverse the entirety of the message. And the final answer for this message, after it's been skip ciphered with a skip value of 3, will be DDCEO. Another method that you can use to achieve the same thing is you can have an infinite series of contiguous messages like decode, 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 and then for each letter you just shift by 3 and just keep on recording whatever you get for the whole message. And using that method, you'll be able to find like the answer to this. Now, getting back to decrypting the message, you simply need to work your way backwards to get the actual message. Again, to show you how it works, we have taken a live example. Here, you can see that how the text gets enciphered using skip ciphers. Link for this tool, as always, is available in the chat box. Feel free to explore this for yourselves. You can see that I've typed a message over here, like this is an example for skip ciphers, and I'm running it with the amount of spacing that I want, and that's the answer that's the output that I'm getting. So you can see this for yourselves. It's really not that difficult. Now we come to the Goliath, right? Many already know what this monstrosity is. The sheer brilliance and complexity of the Enigma deserves a presentation of its own. But for the sake of brevity, let's just glance over a few characteristics of the Enigma router machine. The Enigma machine is a cipher device that was developed and used in the early to mid 20th century to protect commercial, diplomatic, and military communications. It was employed extensively by the Nazi government during World War II in all branches of the German military. The Enigma machine was considered to be so secure that it was used to encipher even the topmost secret messages. Well, this utter beast has 158 quintillion, 962 quadrillion, 555 trillion, 217 billion, 826 million, 360,000 different combinations. Yes, I just did read that number. To even think about storing such a number, you would require 67 bits. Well, that's 3 bits more than what most of our current machines support. I'd like to show you a live demo, right, about how the signals get processed in the Enigma machine. The real one costs upwards of $90,000. And since it's almost the end of the month, I'm pretty light on cash. So to satiate our curiosity, we'll have to make do with a simple simulation. You can see that we first start by taking a random offset for the 3 rotors and run the simulation for the given message. We get to see how the messages are transmitted across from the input to the output lamp pole. So we are doing the message hello. So first we did H, then right now E, again we'll be doing another L, then another L, and then finally an O. And that is how the message gets encrypted using the Enigma machine. Well, if this tickled your fancy, we'd like to recommend the movie The Imitation Game, where the depiction of it is spot on and would encourage you to watch it if you're interested to know how it was broken. Can you smell it? It's in the air. What you might ask? Mystery. Well, there must be many Sherlock Holmes fans in our audience today. But did you know the author, Sir Arthur Conan Doyle, had developed a cipher just to add it to his story, The Adventure of the Dancing Man? In the story, a Norfolk landowner, Hilton Cubitt, and his new American wife, Elise, start receiving strange messages. The messages show dancing men with arms and legs in different positions carrying flags. Something like this. Sherlock realizes that the message uses a simple substitution cipher where a letter is always represented by the same dancing man. He uses a technique called frequency analysis to decipher the message. So again, we'll encode the message hello, H-E-L-L-O, using this method. So you can see that this is how it actually gets encoded. Now, if you want to send a rage-filled message to the Moriarty of your lives, you can use the link in the chat box below to do so. Now, the way it works, that in English, the most common words that are used are E, T, A, O, I, N, S, H, R, D, and L. So an analysis of which stickmen are most frequently used can be used to decipher the message. Holmes realizes what the message says, and it actually says, Elise, prepare to meet thy God, and races to Norfolk. You can make a similar cipher which works on the same position like by yourself too. We genuinely hope that you're not feeling like Sherlock right now. Next, we're going to start with the Freemason Cipher. This is the last cipher that we'll be talking about with historical significance. And at the end of this, we'll give you a small exercise for you to do for yourselves. Well, the Freemason Cipher, or also called the Pickman Cipher, is made by the Freemasons. Yes, they are the same Freemasons who are also colloquially called the Illuminati. This is another symmetrical monoalphabetic substitution cipher, which can encrypt and decrypt using by laying out 4 different grids. 2 grids contain 9 spaces like a tic-tac-toe board. Yes. So like the 2 grids contain 9 spaces like tic-tac-toe board, and 2 grids resemble a large X. It looks something like this. Now what happens is that we fill in all of these, and we use definitive markers like these dots to properly demarcate which one is what. So these sections are uniquely identifiable by a combination of the shape, like you can see over here, the shape of the grid itself, and the specifically placed dots. Now messages can be encrypted using the section identifier instead of the actual letter itself. Well, I told you that we'll have an exercise for you guys today. So I would like to ask everyone present here to try and encipher the word cipher using this Freemason cipher. So for that, I'll give you 2 minutes. So try and encipher the word cipher, C-I-P-H-E-R, right? So try and do it yourselves. So you have got 2 minutes for this. So take your time, no problem. I think that's 2 minutes. So I hope that you guys have like at least tried it out. It's very easy. Like we'll see what the actual solution is, and I'll give you a place where you can like see if your solution is correct or not. So moving on, the use of symbols instead of letters is no impediment to cryptanalysis. This system is identical that of other simple monoalphabetic substitution schemes. So here another simulation we have like got for you. So you can see that we'll run for an example, like this is cool, right? So we'll show you how this actually gets enciphered. So you can see that first of all, this gets enciphered like this, and then is like that, and then finally cool gets enciphered using this like scheme. Now, if you want to see if your solution is correct or not, there is a like a link in the chat box, so you can go and type out cipher for yourself and then see if your solution is correct or not. Now, due to the simplicity of the cipher, it's often included in children's books on ciphers and secret writing. It was also used in the Assassin's Creed 2 game. So, like you can check your solution using the link. Now, let's move on. We start our descent into madness, right? This is something I'm not saying because in this section, we only talk about the absolute basics. The mind-numbing part will be Ariman's job. So don't worry much about this section because it'll get over in a jiffy. Now, let's start talking with talking about prime numbers. Well, modern cryptography would not be what it is today without the usage of prime numbers. We know that many present here already know what prime numbers are, but again, for the sake of not leaving anyone behind and taking everyone for the ride, let's just go over it, right? Very basic preliminary discussion on prime numbers. Well, everyone knows and has somewhat of a basic idea about what prime numbers are. Mathematically speaking, a prime number is essentially a number that has exactly two divisors, 1 and itself. Contrary to popular belief, 1 is not a prime number. You get the idea. So if you want to know more about why 1 is not a prime number, if that is something that you used to think, you can check out the link in the chat box where you'll get to know about why it's not a prime number. So moving on, let us see some interesting properties of prime numbers. Okay, first let's see what happens when we plot them in the polar coordinate plane. Now, a beautiful pattern emerges called the Ulam's spiral. So what essentially happens is that you start taking transpositions of the chord in the system, and then you get to see that slowly this whole thing starts to wrap around itself. And eventually, the state will happen where all of them, all the prime numbers will start to coincide in a single line, all of the prime numbers. That's pretty neat. And you can get to see that we're almost in that, almost close to that state. So anytime now, yeah, I think next state will be there. Yeah, you can see that all the prime numbers, after taking a certain amount of like transpositions, all of them have perfectly aligned into a single straight line. Now, you might have some questions in your head right now, like how are prime numbers connected to cryptography and ciphers? Why should I care about prime numbers? And how long will this thing last for? Well, the answers to which are, we'll talk about it in the next slide. Prime numbers are literally the closest thing to magic in mathematics, and we have no idea, but it's going to be worth it if you stick around. A similar pattern also emerges when you talk about plotting prime numbers using the golden ratio. So here you must be knowing, like you can see the golden ratio in many things, from arches to like the way the sunflower seeds are laid out, and solar panel arrays in the desert, things like that. So over here it's similar to that, and we have just taken and found out what the positions of the prime numbers are, and it also creates a very beautiful spiral pattern. Now, enough about prime numbers. Now let's learn about how to generate prime numbers. The most basic and general explanation is that cryptography is all about number theory, right? And all integer numbers except 0 and 1 are made up of primes. Okay, this is universal fact, right? So before we move on, you need to know that all other numbers except 0 and 1 are made up of prime numbers, and that is the reason why we'll be able to move forward. Prime numbers are important because the security of many encryption algorithms are based on the fact that it is very fast to multiply two large prime numbers and get the result, while it is extremely computer intensive to do the reverse. When you have a number which you know is the product of two prime numbers, finding these two prime numbers is very hard. This problem is called the prime factorization problem. And finding an algorithm which does it in a fast and efficient way is still one of the unsolved mysteries of computer science. Therefore, we must know how to effectively generate these prime numbers to begin with. Well, one method that we use is called a prime sieve. We have all seen sieves, right? Like you use it to that's called colander, but use it to sift through sand and sand and other granular material. So similarly, we'll be having a sieve that actually sifts through all prime numbers, and only ones that are remaining are the prime numbers that we are looking for. There are many prime sieves available to us, right? And the simplest one that we'll be actually going into is called a simple sieve of Eratosthenes. It was discovered back in 250 BCE. Now, the other sieves that might be in your mind are the Sieve of Sundaram, 1934, and still faster and complicated versions of Sieve of Atkin, and various other wheel sieves are the most common. Well, you might ask, how does it work, right? A prime sieve essentially works by creating a list of all integers up to a desired limit and progressively removes composite numbers only till the prime numbers are left. This is one of the most efficient way to obtain a large range of prime numbers. Again, rather than bore you with a lecture of sieve methodologies, let us see how one works instead, not in a memorized or textual approach, but a visual one. For example, if I ask you to generate all prime numbers from 1 to 120, and I tell you to use Sieve of Eratosthenes, how would you go about it? Well, it's pretty simple. So all of the numbers over here are unmarked, right? All of them are gray. So you'll take the first unmarked number over here, which is 2, right? And then you'll add it to the primes list, and then all of the multiples of this number, right, all multiples of 2 will be cancelled out, that we don't want it. Then we'll go on to the next unmarked number, which is 3, and we shall move all the multiples of this number away from that. So similarly, we'll keep on doing this until unless we're only left with the numbers that have only got the values for the prime numbers. So you can see over here, all the pink numbers that we're having right now, all of them are prime numbers, and as sequentially our list also gets filled with the prime numbers. This method has many optimizations, like taking the square root of the upper limit, like taking the square root of 120 and only running this sequence till the square root of 120. And there are many more other optimizations, but I don't want to overburden you with information right now, so we won't go into much detail into that. So, however, if you're interested in knowing more about prime sieves, you can of course approach me at the end of this event, and I'll be more than happy to help you out with understanding about this. So next we'll be just going to CoPrime numbers, right? So if you have talked about prime numbers, we must talk about CoPrime numbers, because since this is an RSA event, our entire thing is kind of based upon the prime factorization problem and CoPrime numbers. Well, in one line, CoPrime numbers are the numbers whose common factor is only one, right? There should be a minimum of 2 numbers to make a proper set of CoPrime numbers. Such numbers have only 1 as the highest common factor. 4 and 7, 5, 7, 9 are CoPrime numbers. CoPrime numbers need not be prime number always. 2 composite numbers like 4 and 9 are also pairwise CoPrime. A fast way to determine whether 2 numbers are CoPrime or not is given by the Euclidean algorithm. It's faster than its faster variants such as binary GCD algorithm, lemma's GCD algorithm, and others. You should wait for Ariman's session for the live code along for more details on these algorithms. The number of integers CoPrime with a positive integer n between 1 and n is given by Euler's torsion function, also known as Euler's phi function. A set of integers can also be called coprime if its elements share no common positive factor except 1. A strong condition on a set of integers is pairwise coprime, which means that A and B are coprime for every pair A and B for different integers in the set. Well, like for example, if you were to take the set 2, 3, 4 is coprime, but it's not pairwise coprime because 2 and 4 are not relatively prime, because you can of course make 4 using 2. Now we'll go on to again some interesting properties. Like you can see the scatter plot, which shows the order of generation of coprimes by using this algorithm. First node 2, 1 is marked in red. Its 3 children are shown in orange, third generation in yellow, and so on in the rainbow order. And it's a remarkable pattern, and it's got somewhat of a very unique look to it. Next, we should talk about like the actual real life example of application of CoPrime numbers. So you can see that in the diagram above, right? If this is a gear pattern. So in the pattern in the gear above, there are 12 and 6 teeth each. So you can see that there are red dots over here, right? Red dots. Those are defects, right? For example, whenever you manufacture something in large volume, like gears, shafts, things like that, there'll always be some defect, right? Always. Now, to minimize the defect, like degrading other parts that it is connected with, we always try and take the the whole array of gears to be a coprime number, and because of that, it minimizes the overall wear and tear that the entire array of parts actually gets. Now you might not believe me, right? So like you can see the simulation for yourself. So you can see that the defect is actually only affecting only one place, whereas in the part where it's not coprime, you can see that many places are actually getting the same defect over and over again. Whew. Congratulations, the boring part is over. Now to the real reason why many people are here, RSA. Before we start RSA, there's one quick little topic I feel that you must go through before Aryaman blesses us with his pro coder skills. That topic being time complexity. Many people must have been wondering what that big O followed by that expression was when we were talking about sieves like 5 minutes ago. Well, that was time complexity. Now, at a very high level, understanding concept of time complexity will be more than enough for us to get started. But for the sake of covering the topic and give you an overview, just here we go. To be concise about it, time complexity is merely a way to represent the amount of time an algorithm takes to complete execution. Some algorithms never terminate and will run forever. We use a Turing machine to determine if such a scenario even exists in our algorithm. Turing machines are beyond the scope of a presentation, but if you're interested in learning more about Turing machines and the halting problem, there is a good resource in the chat box for you to see for yourself. Now, let us try and visualize what all these expressions that we saw earlier even mean. So here, we have created an animation for you to see how many steps are required by an algorithm to complete its execution. So for example, if your algorithm has an input or will require n steps, where n can be any integer, like any positive integer. For example, let's take n to be 50, right? And we have different types of algorithms like n, log n, n square, and so on. So it's better if we see the animation for ourselves. So you can see that over here, if when n is equal to 50, log n will be equal to 3. It essentially means that to complete executing an algorithm with log n complexity, right, it will only take three steps. Think about it like if there is a task, right? If you have a task and you can complete it in 1 day, you can complete it in 2 days, you can complete it in 1 week, but depending on the person, this will vary. So similarly, this also has something similar to that. So you can see that log n takes almost 4 steps, n will of course take 5, and log n will take 195.6, and you get the idea, so on and so forth. So a crucial thing to note is that time complexity of an algorithm or code is not equal to the actual time required to execute a particular code, but the number of times a statement executes. So you may not understand what this exactly means because we don't have any like code right now. But when Aryaman goes through different algorithms, he shall explain what like how we actually determine like what will be the complexity of one and what a step constitutes of. So we just hope that you understood what big O complexity actually means, just like Jim over here, right? So finally, we're here. RSA. What the frack is RSA? RSA, or Riviesh, Shamir, and Adelman, is a public key crypto system that is widely used for secure data transmission and is also one of the oldest. The acronym RSA comes from the surnames of Ron Rivest, Adi Shamir, and Leonard Adelman, who publicly described the algorithm in 1977. An equivalent system was developed secretly in 1973 at the GCHQ, or the British Signals Intelligence Agency, by the English mathematician Clifford Cox. That system was also, of course, declassified in 1997. So if you want to read upon how is RSA different to what Clifford had initially proposed, you can read about it like in the internet. So now the security of RSA relies on the practical difficulty of factoring the product of two large prime numbers. We talked about the prime factorization problem, right? It is essentially the reason why RSA is so secure. Breaking RSA encryption is also called the RSA problem, and whether it is as difficult as the factoring problem is an open question. There are no published methods yet to defeat the RSA system if a large enough prime number is used to encode it. Now, how does it even work, right? This is going to be just a very basic overview on how it works, right? So, let's begin with a fun fact. This section contained originally 6 slides, this section. And after many revisions and thoughtful conversations with the team, we could distill it down to just one anecdote. This is going to be one hell of an anecdote, so brace yourselves for some story time. Let's say you want to tell your friend a secret, right? You're sitting right next to them. You can whisper it to their ear and it'll be okay. But what if you're on the opposite side of the country or the opposite side of the globe? That obviously won't work for you. You could, of course, write it down or mail it to them or use the phone. But each of these communication channels is insecure, and anyone with a strong enough motivation could easily intercept the message. If the secret was important enough somehow, you would not risk it writing down at all, because spies or a rogue postal employee could be looking through your email. Likewise, someone could be tapping your phone without your knowledge and logging every single phone call you make. Well, that's food for thought. One solution to prevent such eavesdroppers from accessing our messages and contents is to encrypt it. Well, this is the basic idea. You add a code to the message which changes it into a jumbled mess, right? If your code is sufficiently complex, then the only people who will be able to access the original message will be the people who have access to the code. Now, if you had a chance to share the code securely with your friend beforehand, then either of you can easily send an encrypted message at any time, knowing full well that you two are the only people who will be having the ability to read the messages and its contents. But what if you did not have a chance to share the code beforehand? This, my friends, is the fundamental problem of cryptography, which is even addressed by such public key encryption schemes, also known as asymmetric encryption, like RSA. So, under RSA encryption, messages are encrypted with a code called a public key, which can be shared openly. Due to some distinct mathematical properties of the RSA algorithm, once a message is encrypted with their public key, it can only get decrypted with another key, also known as a private key. Each RSA user has a unique key pair consisting of public key and its private key. As the name suggests, the private key must be kept a secret. Public key encryption schemes differ from from other schemes where both the encryption and decryption process uses the same private key. These differences make public encryption like RSA useful for communicating in situations where there has been no opportunity to safely distribute the keys beforehand. Let us see an example to understand this concept better. It's a very high level example, so take it with a pinch of salt. Now, imagine this. You are A, your friend is B, like if you are Alice, your friend is B, Bob, and C is a like a person who wants to intercept. He's a hacker, right? Now suppose you're sending a message to your friend. He has his own private key and everyone else, including you, has a public key. So whatever message you had gets locked in a box. And then that box has been locked with the public key and can only be opened with your friend's private key. Suppose an attacker intercepts the box, right? It goes to the internet and they also got the box. Now they only have the public key available to them and they can't open it without the private key that your friend has. So to them, it'll be just a bunch of garbled mess, right? A thing to note is that the passage of data can be intercepted, but without the other key, it's essentially impossible to know what the information is. Even if you did not understand this whole concept, don't worry, we'll get over it in our live demo as well. Finally, the future, where everybody is concerned about it, including my parents. So, homomorphic encryption. Though conceptualized in the 1978, homomorphic encryption is just becoming a reality. A technique that allows for computations to be performed on encrypted data without a key. Homomorphic encryption enables the data owners, the people who have written the data, to encrypt it and not having to not have to deal with any of the other things such as transmission and storage of this thing. Also, there'll be a key which is used to access. When combined with blockchain, homomorphic encryption could usher in a new era of agile, highly resilient cybersecurity and encryption strategies. However, like blockchain, homomorphic encryption requires significant computing power and for now remains prohibitively expensive. Given its potential though, many key industry players such as IBM, Microsoft, AWS are all researching and developing their own homomorphic encryption schemes. Next, this will get my partner Aryaman very happy. Quantum crypto agile solution. Quantum computing is poised to render current cryptography techniques absolutely obsolete. In fact, this is near scientific consensus that quantum computers will be able to break widely used public encryption schemes such as RSA and Diffie-Hellman. Furthermore, the transmission to new quantum resistant cryptographic algorithms will take years to come. Thankfully, we have a head start. Not only are researchers developing new quantum-resistant encryption methodologies, some already exist, like lattice-based, port-based, hash-based, isogeny-based, and multivariate systems, which are all examples of quantum-resistant PKC systems. This is the end from my side. I have to switch trains. So I'd like to call upon my friend and partner and Sasta Keanu Reeves, Aryaman, to teach us the art of coding up our own RSA module without having to use any external libraries in Python. On to you, Aryaman.
Thank you, Ravi, for that. Can you mute him?
Yeah, I can hear you.
Yeah, thank you, Ravi, for that amazing session, part one. I mean, he was talking for like half an hour, but I was the one to take a sip of water there. So, yeah. Now, armed with the knowledge that Reber has given us, let's go straight into the RSA algorithm. So, I hope you guys can see my screen now. Now, we've already covered what, I'll just remove that. So we've already covered what prime numbers and CoPrime numbers are. So let's just dig straight into the RSA algorithm. Now, the first step of the algorithm is to pick two large prime numbers, P and Q. Now, it's really important for these two numbers to be large, otherwise this system won't work. And after picking two large prime numbers P and Q, we need to compute what is called the modulus. So the modulus is denoted by the letter capital N, and you just find it by multiplying these two prime numbers P and Q. Okay. And after that, step 3 is to compute the Euler's torsion function. Now, what is this Euler's torsion function? So we've already covered what prime numbers are, right? A number is prime if its only factors are 1 in itself. And two numbers x and y are coprime if they share no common factors except for 1. Now, this is supposed to be an interactive session. So I want you guys to tell me, are 6 and 9 coprime? Someone just quickly unmute and tell me.
No.
Yeah, exactly, because they share the factor 3. What about, let's say 7 and 9? Are these two coprime?
Yes.
Yes.
Yeah, nice. So yeah, you guys already know this, man. Damn smart. Now let's get to phi. Okay, so phi of n, it's a function. It's just like saying f of x, but you know, mathematicians like being fancy, right? So they use Greek letters like phi. So phi is basically a function of n that returns the number of numbers from 1 to n that are coprime with n. So let's just take a short example. Let's take 6. Okay. So what is phi of 6? First, we'll write down the numbers from 1 to 6. So 1, 2, 3, 4, 5, and 6. So now is 1 coprime with 6? Yeah, it is. And as a side point, I forgot to mention this. The two numbers are coprime if their greatest common divisor is equal to 1. That's one way of figuring it out. Now, 2 and 6 are not coprime. 3 and 6 are not coprime, and 4 and 6 also they share a factor of 2, and 6 is obviously not a coprime. So the two numbers that are coprime with 6 from 1 to 6 are 1 and 5. So what do you guys think phi of 6 will be? It will be 2 because we found 2 of these guys, right? Now we did this on paper for 6, so 6 is a relatively smaller number, right? But we can't do this for like a number with 300 digits. Like imagine doing that. Even a program can't do it. So it can do it, but it will take a while. So we're going to use this lemma. And for all those interested in the math behind this, we have links to the proof at the end. But for now, we'll just be directly using it. So if your number n can be represented as the product of two primes, then you can calculate phi of n with this lemma. So let's just do it for 6 really quickly. Now, how can we write 6? We can write it as 2 times 3, and both of these are coprime. Sorry, both of these are prime, right? And what is 2 minus 1 times 3 minus 1? Someone, come on. It's 2, right? 1 times 2, and that's the answer that we got here. So this lemma works. Now, just to like drill this in, I'm going to use one more example. Let's try to find phi of 14. All right, I'm going to show you that this works. I'm not like trolling you guys. So we'll write numbers from 1 to 14. 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. All right. So now is 1 coprime with 14? Yeah, it is. 2 is not coprime. Now 3 is coprime. 4 is not coprime because 4 and 14 share the factor 2. And since we've cancelled our 2, we can like just cross out all the even numbers there, right? Now 5 is coprime with 14. Is 7 coprime with 14? It's not. 9 is coprime with 14. 11 is coprime with 14, and 13 is also coprime with 14. So what is this? We found 1, 2, 3, 4, 5, and 6. So the answer to this should be 6. And we can also write 14 as 2 into 7, and both of these are prime, right? So what is 1 times 6? It's 6. So this formula checks out. Now let's just go back to our RSA algorithm, okay? So we found out what phi is. So here, yeah. So we found out what phi is. Phi of n, where n is the product of two primes. After that, we're going to choose what is called the public exponent, and it's denoted by small e. And it should satisfy these two conditions. One is it should be between 1 and this phi that we found earlier. And it should also be coprime with phi, which means that the greatest common divisor of e and phi is 1. Now, as a side note, you guys can read this later if you want, but while choosing e, we choose it in such a way that it is prime. It makes things more convenient. And from an industry point of view, e is taken as 2 power 16 plus 1. And now some of you might be thinking, okay, now this is a fairly large number, right? But I was talking about 300 digit numbers. So why is e so small? Now, as you'll see in the next few steps, e is used to encrypt the message. And the idea is that we'll be raising some number to the power e. So like imagine raising that number to the power this number. And we want the process of encryption to be fast, right? That's why this is taken as a relatively smaller number. So now we found that e. And now what we need to do is we need to compute the secret exponent d, right? And this number should satisfy this one condition. So the product of e and d mod phi should be equal to 1. So this mod is like a fancy of saying, the mod operator. So, 5 mod 2 is, what do you guys think this is? How many times does 2 go into 5? It goes twice, right? And 5 minus 2 times 2 is 1. So the remainder is 1. This is like a fancy mathematical way of saying what is the remainder. So now we found d using that formula. Okay. And now here comes the interesting part. Now for those eagle-eyed people out there, you might have realized we're raising this message to the power e. So the message that we want to encrypt, it should be in integer format. So after converting it from, some string to a number, we'll raise that number to the power e and find its modulo n. So find its remainder with n. And that gives us another number, c. And this c is what we can safely give to our friend. And any hacker with, c, they won't be able to retrace back m unless they have the next component, which is small d. So now you've given c to your friend. What does your friend do? He knows what small d is, right? So he raises this ciphertext. C stands for ciphertext. He raises that to the power d and finds that modulo n. So it's remainder with n. And he gets back m somehow magically. We'll see how that happens. So if I lost you halfway there, basically in RSA you have two keys, all right. One is the public key and one is the private key. So what's going to happen is the guy who is generating these two pairs, he's going to release this to the public. That's why it's called the public key. So even adversaries and hackers, they have knowledge of what this number e and n are. And then there's the private key. So over here, n has already been released to the public, right? So d needs to be kept a secret. And in fact, all these four numbers from the algorithm, they need to be kept a secret. P, Q, phi, and d. Because now let's say if the guy has p, right? He already has n. So he can find q and phi, and like that he can find d. So all four of these need to be kept a secret. And as Reber discussed, why does RSA work? It comes down to the problem of prime factorization. When you multiply two prime numbers p and q, you get n. But getting back this p and q from n is really hard. And you might think like, oh, I'll just like run a for loop and check if the number is prime. But try it out. You'll come up with at best an exponential algorithm. And when n is literally 600 digits long, you can't do it in a reasonable amount of time. In fact, to crack this, you would need at least like 300 trillion years for a good enough RSA key. So unless you have 300 trillion years under your belt or a quantum computer, you can't break RSA. Now, what is a quantum computer? That is a topic for another day. All right. So we're done with the steps. Now what we'll do is we'll go to this mini playground and we'll see how this game works. So we have two people, Alice and Bob. Okay. And Bob wants to send some secret message to Alice. So what Alice does is she generates her pair of public and private keys. And this goes to the public, right? So she'll send this to the public. And this is an unsafe channel. So even, hackers and people sitting in like jackets and sunglasses, they're like watching this thing. Okay. So what Bob does is he takes this E and N and he encrypts his message M. And the way he does this is using these two E and N, he finds M to the power E mod N. And now he's found C, right? So he's going to send this C again through that unsafe channel. So what do these hacker guys have? They have three numbers. They have the public key and they have C. But with just these three, they can't decode what C actually means. Because to do that, you need to know what D is. And Alice has kept that to herself, right? So let's try this with really small prime numbers, just for fun. We'll take P as 13 and we'll take Q as 17. Okay. So what is P times Q? What is N? It's 221, right? And what is 5? 5 will be 12 times 16, which is 192. And remember how I said E is taken as like 2 power 16 plus 1? We can't do that, right? Because these two primes are very small. So for now, we'll take E as 5. And as you can see, both 5 and 192, they are coprime. So this is a legitimate value for E. And now you'll ask me, how do we find D, right? So you can do this by brute force, but I think it'll be much better if you use what is known as the extended Euclidean greatest common divisor algorithm. Now, if you do competitive coding, you might know what this is, but I'll just give you like a brief approach of how this works. Now, when you actually code this in, right, you're going to use a recursive function. But since many of you might not be like familiar with recursion, we'll go with this iterative approach. So I'm just going to define these two variables called top1 and top2. And initially their value has to be 5. Okay, and 5 was 192. Remember, 5 was 192. And then we're going to write E. Now we took E as 5. And now we're going to say let small d equal to 1. Now, small d is not 1, but this is how the algorithm starts. Okay. Now what we're going to do is we're going to find some integer k. And we do that by finding the floor division of top 1 and E, which will give you 38 point something. But because of this floor division, we'll get an integer. So at the end, we get 38. And we'll rewrite this k over here, so 38. And now in the next step, what we're going to do is we're going to take that top 1, which was 192, minus 38 times E, which is 5. So how much is this? This is 190. And this is 192 minus 190 is 2. All right. And now we're going to do the same on this side. So again, top 2 was 192. We'll do minus 38 times the current D. So D, we said D is equal to 1. And how much is this? This is around 154. So now what we're going to do, this was the first iteration of the extended Euclidean GCD. All right. So now we're going to take this E and we're going to write it as the new top 1. So 5 and 1. So till here it was the first iteration of this iterative approach. And here's the second one. So this is top 1, which is the old E, and top 2, which was what D was taken as initially, 1. And now what we're going to do is we're going to assign this to a new E. So I'll call this E2, because in the RSA we've already defined E as 5, right? 5. So E2 was 2 as we computed here, and D was 154. Okay. And what do we do after this? It's the same approach. It's just the next iteration. So we find K, which is the floor division of 5 and 2, which is how much? 2. And then we'll write K over here as well, 2. And now we'll find 5 minus 2 times 2. So this 2 times this 2, which is 1. And this 1 is crucial, right? And now we have top 1, which was 1, minus this K times D, which is 154. And this is 1 minus, how much is this? This will give us 308. So this final value is minus 307. Okay. Now we need to keep in mind if at any time D goes negative, now E can't go negative, right? We're using floor division because of the way it works. E can't go negative. But if D goes negative, we'll find that value mod phi of n, which was 192. And the way you do this is you just add 192 until it becomes positive. So that's how it works for negative numbers. And that will give us 77. So this is where the algorithm stops. Okay, as soon as E turns 1, we stop computing. And the value at the end of D is what the secret exponent is. So now let's go back to this playground thing we had. And that was a very long process, wasn't it? So now we found D as 77. So now Alice has done her part, right? Now she'll just send the public exponent E, let's write it as 5, and N, so 221, all right? And now Bob, right, he wants to send some message to Alice, so he's going to send this very top secret classified B, capital B. And the first thing is he needs to convert this string to an integer, and he'll do this using ASCII, all right? So in ASCII, capital A is 65, then capital B is 66, and so on. And small a is 97, and so on. So he's going to take this capital B and he's going to write 66. So now we have our number. Okay. Now what he's going to do is he's going to do 66 to the power E, which was 5, mod 221. Now I can't do mental math, this much mental math in my head. So we'll use idle over here. We'll say 66 to the power 5 mod 221, which is 53. Okay. So this guy gave us C as 53, and now Bob is going to pass this 53 through that unsafe channel. And what does an attacker has? He has 5, 221, and 53. He doesn't know what to do with these numbers, all right? Because he would need that sneaky D, which we calculated as 77. So now what does Alice do? She finds C power D mod N, which is 53 power 77. I mean, can you guys see how huge this is already? Mod 221. So again, we'll take the help of trusty idle. We take 53 power 77 mod 221. And look what that gave us. Can you guys see this? It gave us 66. So Alice knows that Bob used ASCII, right? So she's going to decrypt that string to that integer to string, and she's going to get back capital B. So hooray, that's the RSA algorithm right there on paper. Now let's take some time to implement this in Python, all right? Yeah, that covers the theory part. Let me open the world's best code editor, Visual Studio Code, and we'll create a new file, all right? And we're just going to implement like a dirty implementation of it. So I'll call the file roughwork.py. Okay, and just for reference, what we'll do is, you guys remember these steps, right? We'll dock this to desktop so that you guys can also take a look at what the next step will be and so on. All right. So let's start coding now in Python. We'll assign P to 13. Again, we'll start off with small prime numbers. We'll get to the 300-digit stuff later. And Q was 17. And now we're going to find, what is step 2? Find N, right? So that's P times Q. And phi. Now my keyboard doesn't allow me to type Greek letters, so I'll just type it, which is P minus 1 times Q minus 1, using that lemma that we explored earlier. And now we'll take E as 5, just as before when we were doing the, when we were doing the paperwork thing. So now what is left? We have these, right? We need to compute D. So if you got confused with the extended Euclidean algorithm, we'll go over through the iterative approach. Now, in practice, they actually use the recursive version, but again, I'll just repeat myself. We'll use the iterative approach for now. So we'll assign E2 to E, and we'll say let D equal to 1. Okay. And initially our top 1 and top 2 were 5. Right, so we'll say top 1 is 5 and top 2 is 5. And what was the stopping condition for this whole thing? We did this until E2 became 1. So now this while loop it's going to run until E2 becomes 1. All right, initially it's 5. So what was the first step? First, we'll find that number k, right? Which was given by top 1 divided by 5. Sorry, E2. Yeah. So if you guys remember what we did on paper, what we did was this was 192 divided by 5, which gives us 38. So that's like this is a comment line, it won't get executed. And now what I'm going to do is, you guys might have covered exchanging two variables, right? And to do that, if you're not using Python, what you do is you declare a temporary variable. So we're using the same temporary variable concept here to store the old tops. Okay. So we'll say old top 1 is top 1 and old top 2 is top 2. And now what we're going to do is we're going to assign E2 to just a second. Yeah. Old top 1 minus k times. What have I done over here? Sorry, my bad. This is why it got messed up. So if you guys remember, in the next step, right, we assign in the second iteration, we assign top 1 to E2 and top 2 to D, the old values. And now we can replace E2 using that old top that we stored in the temporary variable minus k times E2. And D will be equal to old top 2 minus k times the old value of D. And what was that one condition? Do you guys remember when D went negative? So that kind of messed things up, right? So we'll put one if statement, which will say if D is lesser than 0, if it's negative, then just find assign D to D mod 5, where 5 was 192. And that concludes the extended, I'll just write it here, extended Euclidean GCD. Okay, you guys can Google the recursive version. That's very elegant. Yeah. And when you're programming, you can't get everything in one shot, right? So you have to like print once in a while to see if everything's working or not. So we'll print the RSA components. So first we'll print P, and then we'll print Q and N, which we found in the second step. We'll also print phi. And what else is left? We'll print E, that's the public exponent, and D, which is the secret exponent. And if you guys remember the paperwork stuff, this should have been 77. So fingers crossed. Now I'll just run this, and it's going to take its sweet time to run the code. Yeah, there you go. So these are the RSA components. Now, this whole thing was actually Alice's part, right? She's generating the key. So now we'll move on to what Bob will do. Now, obviously, in a real life scenario, this whole code won't be in one file. That would be dumb. But this is what Bob would do at his end. He would have, I'm going to create a function called encrypt. Okay, if I can spell encrypt. And that's going to take two things. What are the two things needed to encrypt something? You need the thing that you want to encrypt, that's the plain text, and you need the public key. So I'll pass these two parameters. All right. And before we write encrypt, this is what it's going to look like, right? We'll say plain text is equal to capital B, because that's what we did in the rough work thing. And our cipher text, which is what comes out when we've encrypted, will be the result of whatever this encrypt gives us. Okay, so that's plain text, comma, E. So basically what I'm doing here is, this is a list, right, in Python. And I'm passing these two parameters, small e and capital N, because that's the public key, right? And then we'll just fetch these two. So we'll say E is equal to public key. I could have just passed E and N, that could have also been done. And public key of 1. So now we know how to, now we know that this function will give us the encrypted value of B, which was 53, if I'm not wrong, when we did it on paper. And okay, now how do we do this? So when you have a message that's like BA, the number that you want to get is 066097. All right. So the way this works is first B gets converted to its ASCII value. So then we'll get 066. And then it's going to give us 097. So to do this in Python, we'll say cipher text is equal to an empty string. And what we're going to do is we're going to loop over this plain text. So we'll say for I in range 0 to the length of this plain text. And this loop basically runs how many ever times as the number of characters in plain text. All right. So I'll just take one character at a time. So we'll say plain text of I. So for this BA, this loop will run 2 times, right? And in the first time we'll get capital B, and in the second iteration we'll get small b, small a. And now what we'll do is we'll use this funny function. It's called ORD, okay? So this ORD takes one character and it returns the ASCII, or technically the Unicode value of that character. So if we give it capital B, this is going to convert capital B to 66, okay? And this 66, keep in mind, this 66 is now an integer. This function returns an integer. And what we're going to do is if ch is lesser than 100. So now let me explain it this way. All right, we have 66, but what is the ASCII value of small a? It's 97. And eventually your characters are going to have values that are greater than 100, right? Like M and all that, all those letters out there. So when we're decoding it, we want to parse it in block sizes of 3. So if by chance this character is lesser than 100, we'll just add this like dummy variable 0. And what I'm doing now is called string concatenation. All right, we're first converting this 66 to a string. So over here, that 66 will turn to a string. And then I'm adding this dummy variable. So at the end, what's going to happen is this will become 066, that we can later extract it in block sizes of 3. And if this is greater than or equal to 100, then we can just directly convert it to a string. And remember this empty string that we declared ciphertext? What we'll do is we'll just append this plus equal to ch. And this is already a string, right? So now that okay, so what this does is, remember BA, right? At the end of this whole Mahabharat, what we're going to get is this number as a string. So this whole process was just to convert the string to an integer. And now remember that M from here. This M is what's going to be over here. All right. And now we can actually find C. So we'll say C is equal to, with this formula, so M to the power E mod N. So you guys saw me do it this way in idle, right? But actually we shouldn't do it this way, because for an n that's going to be greater than 600 digits long, this is going to take forever. Okay. So instead what we'll do is we'll implement Python's power function. Now why this function does it faster? If we have time in the end, I'll explain that. Just drop me a message and I'll give the explanation there. So what we're doing is we're finding M to the power E mod N with this power function. And that right there is the ciphertext. This should hopefully give us 53. And now we'll return the C. So when Bob gives this C to Alice, he wants to give like a string, right? So we'll just convert it to string and then we'll return that value. So as I said before, we need to test our code and see if it's working at like intermediate steps. So I'll say ciphertext and we'll just print this value. So this encrypt function should hopefully return 53 for the example that we've given. And there you have it. That actually worked. Why do I sound surprised? Yeah. So now Bob has this 53, right? He's going to send this to Alice, all right? So now we'll define, as we defined an encrypt function, we'll define a decrypt function. Decrypt. Okay, so what will this take? This will take the ciphertext as a string, and it will also take the private key. And this is something that only Alice has, right? So she's going to take D from this private key and capital N, private key. And okay, now let's think of this in reverse terms. All right. So before we got 53, and what we did was we did this power thing at the end, right? But when we're decrypting, we want to do it in the beginning. So what I'll do is I'll just say C is equal to int of ciphertext. So now we've converted it to an integer. All right. And now what we'll do is, yeah, this is where we'll apply this function, this formula. We'll say m equal to power of c comma d comma n. So this power thing, just to reiterate, it's going to give us c to the power d mod m mod n in a much faster way. That's why we're using power, right? And what will this give us? You know, at the end of this, m will be 66. But as I said before, 66 won't work, right? Because we want to parse it in blocks of 3. So if by chance the length of m is not equal, if the length of m is not divisible by 3, so if the remainder is not 0, we'll say m is equal to, again, we'll add that dummy 0 over there, plus string of m. So this was 66, right? This was 66 as a number. Here it turned into 66 with quotes, and here the dummy variable 0 got added to it. So now what we have to do is we have this like huge number, right? It's as a string. So we need to parse this. And what do you do to parse a string? Again, we need another for loop. So I'll say for I in range 0 to till the end of the string. So that, and here I'll give an increment of 3. So the first time we used this for loop in encrypt, we didn't need an increment, right? Because we were going character by character. But now we're going in blocks of 3. That's why I'm giving this increment of 3. So I'll say character is m of I, and here I'm using a concept known as list splicing or string slicing, whatever you want to call it. So check that out if you guys don't know what this means. Basically, what this is going to do is it's going to go over what was it for BA? For BA, the number was 066097. So in the first iteration of this loop, CH will become 066. And in the second iteration, it will become 097. Okay. So now what we'll do is we'll find the, okay, now we have a number and we want to convert it back to, we have the ASCII value of the number and we want to convert it back to its letter. So if we have 66, we want to get back that capital B, right? So first we'll convert this string to an integer. And then we'll use this CHR function, and that does exactly that. And what we're going to do is, before this loop, we're going to define an empty string, and we're just going to append this to that empty string. So in the first iteration, this part extracts 066, and this becomes, after this step, it'll become capital B, and it'll put capital B in this empty string. And then it's going to take 097, and then it's going to convert 097 to small a, and then it's going to append that to the message. And then we just have to return this guy. So we'll say return message. So now let's call decrypt. So up till here, everything worked fine, right? We got 53. So now I'll say, let's say the message that Bob wanted to send is whatever decrypt returns on ciphertext and the private key, which will pass it in this way, in this list. So over here we have d comma n, right? So here it's going to extract that d comma n and use it to decrypt. And hopefully by the end of this, we should get back that capital B that we wanted to send. So yeah, now I'll just execute this. And it's telling me that, let's see, object has no, wait, where's this line? If len of m. See, so here's a rookie mistake. I tried to find the length of a number. So len works only on strings, right? Yeah. Now let's run that again. And boom, it gave us capital B. So now our encryption works. Yay. So is that the end of it? Not exactly. You need to make sure that strings apart from this top secret B work. So let's try sending hello. And now I'll just execute this code. And that gave us 8. So something went wrong, right? Obviously. Let's try something smaller. We'll try that BA that we've been talking about this whole time. And it's giving us this, what is this arrow? So this brings us to the first limitation of RSA. Okay. The size of the plain text that you can encrypt is actually limited by the initial prime numbers that you use. So here we use these like toy prime numbers, right? Like what is this 13 and 17? It's just too small. So for your RSA encryption to work, the length of your message needs to be smaller than n, this number, right? So what we can do is to encrypt larger messages, we can use larger primes. So I have that stored over here. I'm just going to copy this, and I think we won't need this part now, right? So I'll just say, okay, how does this work? Yeah, there you go. So we'll just copy these two really large primes, and we'll comment these two noob level ones, and yeah, there. So can you guys see the scale of this? This one prime is 300 digits long, right? We're writing code that can actually play with these two. So in RSA terminology, when P and Q are around 300 digits long, we're generating what is called a 1024-bit key, because the n that we get, it'll need 1024 bits to store this guy. And from like an industry point of view, they use 2048 bit. That's like the recommended one. So even these numbers are small. Yeah. And again, we need to change E, right? Again, since we're trying to replicate the industry, we'll say E as 2 power 16 plus 1. And now let's run this code on the letter BA. And okay, so first of all, our screen just gets bloated with all these numbers, but at the end you can see there's this tiny thing that says BA. So I should have put some spacing while printing, but these numbers are so huge, right? Like look at P and Q, it's massive, and N itself is a 1024-bit key, and there's our good old E over here. But the message worked, right? It got encrypted correctly and decrypted correctly. So now what we'll do is we'll pass something greater, right? Like we don't want to send 2 or 3 letter things. So I'll send hello world, like any typical programmer would, and we'll add some like complexity to this code, okay? And now let's execute that. So as you can see, the final thing that we print is what we get after decrypting it. So encryption worked, decryption worked, and it gave us back this original message with these special characters. So I just like to note that this code that we've written, it won't work for all characters, right? Like it won't work for the rupee symbol and things like that, because we've done it in blocks of 3. So yeah, that's it for the RSA algorithm. What we were going to do is we were going to create this module of our own with like proper functions, and this was like a dirty implementation, right? Don't show this to your potential employer. He'll say that you can't write code. So this is like a slightly more refined version. And here we've used file handling. Okay. So this was the module, and this is the main function. So if you guys are interested, you can implement something like this in the future. So now if I run this app.py, it's gonna welcome me to this RSA app. And first is let's enter 1. So what will 1 do? It will generate a pair of public and private keys. So we'll do that. and it will tell us that these keys have been generated. And if you can see at the top left, these two files have been generated. So this is the private key, where this is D and this is N. And this is the public key, where, as you can see, we find our good old E over here, 2 power 16 plus 1. It's a very good prime to use here. So after generating them, we'll load these two keys. So these two keys have been like loaded into the program. And now we'll say 3. So let's encrypt something. So let's say, again, we'll use a very original text to encrypt. Let's say hello world. And that gave us this guy, right? So now what I'll do is I'll copy this and I'll say decrypt. And then I'll paste the same string. And we get back hello world. So what you can do is you can actually try this out. So I'll decrypt the same thing again, right? But instead there was a 4 at the end. Do you guys see this 4? So instead of that 4, I'll write 5, okay, and we'll see what it decrypts. So a simple message, hello world, turned into this huge string of gibberish, right? So any potential attacker, he needs to, and even you yourself, while you're decoding, you need to enter the right string to decrypt. So here's the right string, and it'll give us back hello world. So I think that pretty much wraps up the RSA part of this. I hope you guys understood this. We'll be sharing these codes and also these lovely notes. So if you guys don't understand, any of the math part or my handwriting, you guys can tell me and we'll help you out, right? Do you guys have any questions?
Hello, myself Kartik Nigam.
Yeah, hi.
Actually, I have a confusion like the number P and Q. Where did you get that 300 big digit number?
Oh, that's a really good question. Okay, so actually, dude, that's a really good question. So here, right, for this I used a website. I'll send you the link, okay? You can just generate, I just told them that I needed a 300 digit thing and it gave me the number. But there are algorithms that have been developed to generate these large primes. And if you remember Reber's part of the thing, he explained the sieve of Eratosthenes, right? So these aren't like random jargon terms. These are actual terms that you learn in like DSA and things that you use in competitive coding. So one of the algorithms is the sieve of Eratosthenes, or I hope that's the right spelling. Or you can use another algorithm. Like what you can do, let's say you want a 1024-bit key, right? So we need P to be like half of that, right? So 512, we need like a 512-bit number. So what we'll do is we'll just take, in Python, there's this random library. So we'll say import random, and using random.randint, you can specify two numbers, right? So 2 power, let's say, what was the number? 1024. So 512. So 511 to 2 power 512 minus 1. So like this, you can generate a number, okay? And that number, it's a random number, right? So there's a good chance that it won't be prime. So after generating that, you can keep incrementing it by 1 until you get an actual prime number. So for that, you'll have to implement like, you do this in college as well. You'll have to implement like an isPrime function, which returns true if the number is prime and so on. And there are many ways to generate prime numbers, man. We can have like a session on that itself. Yeah. So did that answer your question?
So there can be different values of P and Q, like we can generate any
yeah,
such a big number.
Oh, you need to. Okay, so now I'd just like to mention one more thing. Before we generate P and Q, right, we choose E. So E is 2 power 16 plus 1. That's like an industry thing, right? And then we generate P and Q, and then we get phi. So E and phi need to be coprime. So when you're randomly generating two primes P and Q, there's a chance that you generate phi that is actually not coprime with E. Now, in which case will that happen? E is prime. So if phi is a multiple of E, then phi and E won't be coprime, right? So in that case, you'll have to put a check, okay? In that case, your P and Q are like invalid. You can't really use them. So you'll run that generating algorithm again, and hopefully you'll get a better set of P and Q. Yeah.
Okay.
Also, Karthik, like one more thing, if you're trying to generate like a stupendously big prime number, right? So rather than like you can obviously generate like random numbers from that and keep on incrementing. But mathematically speaking, if you are like more inclined towards actually finding out a very short way, there is a method called Miller-Rabin. Okay, Miller-Rabin. You can. What happens is that there is a definitive mathematical formula. Okay, like remember the the spirals I was showing. So like when you see the different ways they usually project into the future, like the way the spiral extends, you can actually predict where you will find the next prime, the near vicinity. And because of that, you can generate like very large prime numbers, like maybe 4096 bit prime number, like in a minute or something like that. So they like these kind of algorithms are there. So again, if you want to know, the algorithm's name is Miller-Rabin, Miller-Rabin. Okay.
Yeah, thanks, Rebbe. That's a really good one.
Hi,
So-
I'm Sahar.
Hi, Sahar.
I have a question. Do other encryption algorithms like SHA-256 or MD5 work in the same way?
I think Rebbe, do you want to answer that?
Yeah, I can tell
Like
you about.
I've encountered these things called PGP keys, where
Yeah.
they generate the same key value pair. They're used for signing and for encrypting.
Yeah.
So see, like recently, I understand like what's your question, right? So you want to know how do they work? So essentially, what happens is that like recently I was locked out of my GitHub account, so I had to generate like a SHA-256 bit key for my machine, and I had to validate that and had to see if it was working properly or not. So see, what essentially happens, right? SHA-256 is more of a pseudo-random type algorithm, right? And it is very secure. Like it's very secure. And what PGP keys are also used for, right? Like they can be used for good things and bad things. Like most of you guys might have heard about like the dark web, right? So like when you place orders on the dark web, you usually place them through like a encrypted PGP end-to-end encryption key, and uske through you actually do the communication. And as far as like how they work, well, again, like I said, it's pseudo random. Okay, like you cannot find a proper pattern to this. I think there was a very nice bike-leak analysis for this and AES-256, like to break them. I think it was done in 2017 or 16, and like they could somewhat make like somewhat of an idea ki how to break it, but they could not fully. There is, however, one algorithm that can break any type of even pseudo random, even like RSA and like AES diff element, like I said.
Shor's algorithm.
Shor's, yeah, exactly. So Shor's algorithm. Yeah, when you, it's a quantum, it's an algorithm that
quantum computing algorithm.
Yeah.
So you can use that to break it as well. So I think that I hope that answers your question.
Actually, like computer Shor's
it does.
Right. Like we did complexity classes, right? So you guys saw those curves. Like this was constant, polynomial, and exponential. So factoring is actually an exponential problem. Okay. And Shor's algorithm turns it polynomial. So, n power something. And this is like a
also,
huge yeah.
One more small thing. There's this, Riemann's theorem. Like there's a
hypothesis.
$1 million problem. Yeah, Riemann's hypothesis. Sorry.
Yeah.
That predicts the location of primes. So will a theoretical solution to that affect these algorithms?
Yeah. So here's the thing: we don't know if the Riemann hypothesis is true or not, right? So even if it is true, even if we can predict where these primes are, right? We're not sure whether it will affect RSA itself. Like, see, for example, this Shor's algorithm, right? It has been mathematically proven to break RSA because it can factor quickly. But Riemann's hypothesis hasn't yet been proved. So, yeah.
See, also like when you're talking about similar algorithms, right? So since we've entirely glossed over the whole thing about modulo, right? We can do a whole like a whole presentation on modulo itself. Like there's like modulo multiplicative inverse. There's things like Fermat's little theorem, right? There are many things, and you can incorporate like modulo multiplicative inverse and its concepts into RSA to make it like make generating stuff way quicker. So like there are these things, right? Like for example, like if you're talking about things that have been unproven, have not been proven, you can talk about Fermat's last theorem, right? You don't know if it's true or not. So it's just conjecture at this point. We actually don't have an idea. So that.
And yeah, since like remember I promised you guys that I would explain like why we use pow and why we don't use that star thing. So I'll give like a slight hint. Okay, basically this is something from modular arithmetic. So a mod b mod n, it can be simplified as a mod n times b mod n times sorry, a mod n, b mod n, and then that value mod n. So this is like basically this number can be like insanely large, right? But because we've put this cap on a and b, this multiplication becomes much faster and this whole process gets like speeded up. Yeah.
So also one more thing that like we usually like we can implement over here also, that is like to make the whole multiplication thing possible, right? Usually if you're talking about like multiplying two numbers, like for example, if you're multiplying on your machine right now, it will take n squared time to multiply the two numbers, unless you use like a better, faster method like Karatsuba's multiplication, which I think turns it down into like linear time, right? Converts the whole thing into a string, and then you do all the like shifting of the numbers from there. Also, one more thing, like a very curious thing that I would like everybody to explore after this is, since we're talking about modular arithmetics, right? So like mod a, like a plus b mod n is a mod n plus b mod n whole mod n. Similarly for like a minus b mod n. Similarly for a into b. But when you try and divide like a by b, it breaks. This whole thing, it just breaks. It does not make sense. So for that, you can like see like by one very nice way of thinking about it is like the one that Fermat gave us. Okay, like Fermat's little theorem, it's called. So again, like we would encourage you to go and try and see this for yourself. It's amazing. Like, if you're inclined towards mathematics, theoretical mathematics, or generational mathematics, I think it's perfect.
An additional question, like usually when you're dealing with computers and programming languages, there is a little inconsistency when it comes to large numbers. For example, when you say divide numbers, you get, instead of like if I print 1 by 2 in with like
talking about precision in division in computers.
This thing,
yeah,
right?
yeah, exactly. Yeah. So how do encryption algorithms deal with this?
See, honestly, we don't deal with many many divisions in this, right? There aren't many divisions that we're doing. We're mostly multiplying. So
modulus itself is a result of division, right?
We're using integers, right? Like we're using integer and floor division. So this whole idea of like floating point, it doesn't apply here. Yeah.
Okay.
And one more thing, like just to add on, in Python, right, you guys might have noticed like we just like casually wrote this huge number. This would not be possible in C or like a statically typed language, which is why we chose Python. Because like C, you have to declare like int a is equal to, and then that a can't be greater than max value of int, or long. Even long can't hold this number. So yeah, because of the way Python does it, we could do it here.
In C++, you can maximum give for long is 10 to the power 19, and for like normal integer, I think it's around approximately 2.7 billion for normal integer.
Yeah.
But since these are positive values, you can do unsigned and effectively double it, right?
You can, but you can't store like a 600 digit. Oh yeah, I'll tell you how you can do it in C++. You can declare an array, okay? So you'll have to say like int a is equal to new int, and then like if you say 300, then each value in the array will be one number. So that's like one way you can do it in C or C++.
Yeah. Also, one more thing, you can do this whole thing in C++ in equal or even faster than this. If you were to convert everything into a string, stringify everything from multiplication to extraction to everything, just consider it to be a string, and I think you'll be good to go.
That's very interesting to know. Thank you.
No problem.
Thanks for those questions. Some really good questions there. Yeah. So I hope you guys enjoyed this session. We'll also link you Reber's Code Forces account so that you can stalk it later. Yeah.
Okay. I think that's it. Any other questions? Do you have anything else?
Yeah, I have a question.
Please go ahead.
In the movie The Imitation Game,
Mm-hmm.
did Alan Turing really play with like quintillion of values to break Enigma?
Okay, I'll tell you how they broke Enigma. I'll tell you. See, the Germans, okay, after each message, they would write "Hail Hitler."
Yeah.
So
Yeah,
basically,
I've seen
there's
in the
like this.
movie.
Yeah,
Good
yeah,
evening
yeah.
and Hail Hitler. Hail Hitler.
Exactly. So what he did was okay, now this is getting into deep learning, okay. He created like a perceptron, like that huge machine, right? It's basically like you can call it like a basic neural network, very, very basic version. And that learned the patterns, like basically you need the first message, right? The good morning and the Hail Hitler message. So using that perceptron would figure out the key combination, where the rotor should be rotated. And then they would rotate that, and from there they would like get back all the other like encrypted stuff. Yeah.
So he basically just smashed in a million different combinations and then.
No.
Not a million, because see, it was very optimized for his time, because right now currently we have the computation power to brute force. I'm not kidding. You can brute force Enigma currently. If you're using your current laptop, you can easily brute force Enigma. But back in the day, like maximum you can run about like maybe one operation per second. That was very slow, right? You could not think about doing it. So like Ariman pointed it out, you would just they did a pattern analysis. Ki, acha, I have got the a given length and I know what the answer is going to be. So what possible combinations can I get to this answer? That was the basic gist of how like they broke Enigma.
It's like,
so he basically worked back.
No. Let me put it this way.
He worked back from the.
Yeah, that's one way. But like, okay, see, if you show like a 4-year-old like 3 pictures of a dog, okay, you show him the picture. This is a dog. You show him another picture. This is a dog. And you show him one more picture. This is a dog. For the rest of his life, he'll be able to identify dogs. We didn't have to show him like 100 or 1,000 images, right? So in a similar way, this perceptron, like from just that Hail Hitler and that end part, it was able to figure out the entire combination, or at least enough to like decode a few words. That yeah.
And since like I said, it's a polyalphabetic substitution cipher. If you just get even one correct alphabet, you're basically set for the others. So breaking Enigma was a big deal back in the day, but if you can just figure out the correct answer for one letter, bro, you're done for all of them. It's basically broken. Just one letter and you're done.
Yeah, I guess that's it for now, guys. Thank you all for joining and for listening patiently. I hope you guys enjoyed this whole thing. Yeah.
Thank you, guys. Thank you.